Welcome to Ready to Derive. In this video, we're going to be looking at optimization, which is a really cool application of calculus. And all we need to be able to do is to work with derivatives. But this has some practical applications in the real world. Here's some questions you might want to answer using optimization. How could we maximize the area of a given region? Or how could we minimize the waste in producing an item? How can we achieve the largest revenue? And what is the shortest distance between two objects? And these can all be answered using calculus, because if we can model area or waste or revenue or distance with a function, then what we're really looking for is just the location of the maxes or mins of that function. And in both cases, so max or min, all you really need to know is where is f prime equal to 0. So this is the fun we have to look forward to. And without further ado, let's get started. So we're going to start with a classic optimization problem, which you find in most textbooks. So here we go. An open top box is to be made by cutting a square from each corner of a flat rectangular piece of cardboard with dimensions 8.5 by 11. So let's get that. So this width is 8.5 and this length is 11. And we are going to cut a square from each corner. So they're going to be the same congruent squares. Cut those up. Cut those off, I mean. And then what we'll do is we'll fold along these edges to make an open top box. So what will that look like? So here's the front of the box. Here's the back. Just to help us, this is a great way to draw three-dimensional figures. If you have trouble with that, draw a rectangle and then draw a congruent rectangle behind and then just connect. And you can use dotted lines for any edges that are in the back of the box, the so-called back of the box. And so here's the thing. This is a little twist on the classic problem, because we're not going to waste those 4 squares. We're actually going to use them to make an additional storage object, a cube. So here we have, let's draw a little cube on the side. Let's connect. Once again, so those 4 squares are just this cube is not going to have a top or a bottom, but it could still use to sort of store lightweight things. So and the question we're going to ask is, what is the maximum combined volume of the box and cube that could be made? And so to actually maximize anything, we of course need a function. So we need to define the combined volume of the 2 objects. Now, if this length is 11 and we are taking off, let's see, we need a variable if we need a function. So let's call the x the length of the side of the squares. We're taking off an x from this end, an x from that end, which is going to give us this length as being 11 minus 2x. Similarly, this length will be 8.5 minus 2x. And because we're folding it up by that amount, this must correspond to x. So the volume of that open top box would be 11 minus 2x times 8.5 minus 2x. And I'm just going to multiply by x the height in the front here. So that's just length times width times height. Now, the dimensions of this box, because they're made from the squares, is x, x, and x. So the volume of that box would be x cubed. And now we have a function for the total combined volume. So let's call that volume formula up there. And before we start to analyze to figure out what the maximum volume is, we want to think about the domain of the possible values of x. So we know what to restrict our attention to. And we can kind of agree that x for a start better be sort of greater than 0, because otherwise we're just not going to have any boxes. But is there an upper limit to what x could be? So let's take a look at the function here. We obviously need 11 minus 2x, for example, as we need x to be greater than 0, we need this to be greater than 0. We don't want a negative length. Well, if you solve that, you'll get x is less than 5.5. So you might think, well, that's our upper bound for x. But if we repeat that for this parentheses, we'll actually find that x has to be less than 4.25. So that becomes our upper bound, and we will restrict our attention to values of x in that range. So I've just saved us some work by foiling that out and combining like terms just to simplify that volume function. And then what do we do next? Well, clearly, if we want to optimize, make this the maximum volume possible, we need to find the critical values of this. We need to find v prime x and set it equal to 0. So let's do that. That will become, by the power rule, 15x squared minus 78x plus 93.5. And we set that equal to 0. And this is not factorable, not easily not factorable by hand, but you can use a quadratic equation solver and you will get these two values, 1.87 and 3.33, both of which are in the domain. So we can treat them both. So now the best way to approach this is to use the candidates test to consider the possible values of x. Now I realize that we think x has to be, we know x has to be greater than 0, but I want you to humor me for a little bit, and let's just include those endpoints and see what happens there. So we put those, this is the candidates test for finding the absolute max over or min over a closed interval, and we put those critical values in there, and then we find the volume at those, and you can just use a calculator to confirm this. If you plug in x equals 0, obviously the volume is 0. 1.87 for x, you get a volume of 71.2, 63.5, and so far 71.2 does look like the maximum, the absolute max. So here's the twist, is that if you plug in 4.25, the volume, the combined volume, comes to be out to be 76.8. So what would your conclusion be? The maximum combined volume of the boxes is 76.8 inches cubed, and that's achieved by cutting off squares of side 4.25 inches. But let's actually look at what's going on here. So imagine that we came in here and we took off squares of side 4.25 inches. Well, this is 8.5, the width of the cardboard. So 4.25 is half of that. So 4.25, if we cut off squares of 4.25, so there's the one square, there's the other, right, 4.25. Oh, it seems like we're going to run into a problem because we have nothing left to make the open top box with. So we are in a situation, we have just discovered that, in fact, if you really want to make the absolute max combined volume, you would use 4.25 as the side of the square you cut off, and you get a massive cube. You get no open tray, no open top box or tray, but instead you get just all cube. But that does answer the question. That does indeed deliver the absolute maximum combined volume. So we'll finish up this opening problem by looking at a graph of the function, just to illustrate what's going on in the candidates test. And so here we can see that, yes, indeed, this point here, when x was 4.25, we did indeed get the maximum combined volume, except we get no open top box, so that this answer here is the more realistic answer if we would like to actually achieve both boxes being created. So this would be our final conclusion. If you actually want to create both boxes, then the maximum combined volume will be 71.2 inches cubed, achieved by cutting off squares of side 1.87 inches. So before we dive into more practice problems, let's get an overall optimization strategy together. So the first step is always to define the function that models the quantity you need to maximize or minimize. In terms of one variable, and let me explain that. So the volume function we came up with in the previous example, well, it was just in terms of x, so we didn't have any work to do. But sometimes it might be more than one variable, and then we have to use any constraints in the problem to re-express the function in terms of one variable. We'll see an example of that moving forward. The next step is to use the first derivative to identify the critical values of the function, because this is where we know that possibly the max or mins will, maybe not the absolute max or mins, but possibly those are the candidates. So we then, step 3 is to identify the domain of the problem and establish the location of the max or min of the function. So if the endpoints matter, then obviously you would use the candidates test to compare the values of the function at the endpoints versus at the critical values. And if the endpoints don't really matter because they don't give realistic situations, then we can just use a second derivative test as an alternative. And step 4 is to write a conclusion in the context of the problem. So here's the first practice problem. We would like to find the rectangle with the largest area that kind of fits under this parabola and sits above the x-axis. So it's going to look like this. And the first step is to define the function in terms of one variable. So this is where it gets a little more interesting. So what variables am I going to use? Well, it seems like x and y are when we're on a coordinate grid, why not start with x and y? And let's think about what the area of this function would be, of this rectangle would be in terms of x and y. Well, this distance here, this would be the x coordinate, and this here would be the height of the rectangle, and x would be half the length, so because this would be x as well. So therefore, we know that we can write the area as the length, which is 2x, times the height, which is y. But we also know that we have to express it in terms of one variable. So we are going to express it, let's do in terms of x, because if we look up here, we actually already have y expressed in terms of x. So we can make that substitution. So 2x, I'll just change colors, and then here in place of y, I'm going to put this. And while we're at it, maybe we could just multiply through just to simplify. Okay, anticipating the next step, which is to find the critical values. So we find the derivative, which is 6 minus 3x squared. We set that equal to 0. So we get 3x squared equals 6, x squared equals 2. And so x could be technically the square root of 2 or the negative square root of 2. They're kind of symmetrical, so we don't really need to consider them both. So right now, because we are talking about length, we want to keep that positive, and we'll settle with x equals the square root of 2 as our critical value. So let's continue with this example. Step 3 is to find the domain for x and then carry out the appropriate tests. And I hope you can see that x would certainly have to be bigger than 0, because if you just look at the area function, if you put x equals 0 in there, you don't get a rectangle with 0 area, so that's not going to be useful. Is there an upper limit to what x can be? So x has to be greater than 0, so we could, to even make a rectangle, so x could be just a little bit bigger than 0, and we could have a rectangle that looks like this, or x could be maybe 2 point something, maybe that big, and we'd have a rectangle that looks like that. But obviously there's a limit to what x can be, because otherwise we won't get a rectangle again, and that's going to occur at the x-intercept. So let's find that x-intercept, and that would be 0 equals 3 minus a half x squared, 3 equals a half x squared equals 6, x equals the square root of 6, and so therefore, and that is about 2.45. So we realize that x has to be between 0 and 2.45. But notice that the endpoints don't really count because they don't generate rectangles. So as our critical value is square root of 2 is approximately 1 point something. Yes, it's in the domain. So the next thing we have to do then, if rather than use the candidates test because the endpoints don't matter, we can actually just use the second derivative test. And this is a prime, so a double prime. The second derivative would be just negative 6x. And we know that x is root 2 is positive, so we know that's less than 0. In fact, for any value, a positive value of x, the second derivative is going to be less than 0. So that means that the function a of x is concave down when x is greater than 0, which means that x equals root 2. So it's concave down for x greater than 0. So that means x equals square root of 2 is location of maximum. All right, so at that point, we can make a conclusion. Now, we did need the dimensions of the rectangle, so let's not forget we have x equals root 2, which means the total width is 2 root 2. remember, because it was 2x was the total width. So now we just have to find y, but we have the original equation of the function, so we just put in root 2 into here. Root 2 squared is 2, times a half is 1, and so 3 minus 1 would just come out to be 2. And so we can make our concluding statement. The rectangle with length 2 root 2 and height 2 will have the largest area. For our second practice problem, another classic optimization problem. So a cylindrical can is to be made to hold 1 liter, 1,000 centimeter cubes of liquid. What are the dimensions of the can that will require the least amount of material to construct? Well, the dimensions, now we're not dealing with length and width. For a can, we're going to be interested in the dimensions, the radius of the base and the height of the can. So we have to define a function for that which we wish to minimize, and that's surface area. So the surface area, so this formula would generally be provided to you, but you notice that the surface area formula is in terms of 2 variables, and we need to get it in terms of 1 variable. So we have to identify the constraint in the problem, and the constraint is that it needs to hold, this can needs to hold a volume of 1,000 centimeters cubed. And so we need to use another formula for the volume of a cylinder, pi r squared h, and we need to put that information in. So we know the volume is fixed, it's 1,000 equals pi r squared h, and we want to replace preferably h in terms of r, so we're not going to have to deal with any square roots. So let's isolate h, and we get this. And now we can go into the surface area formula, and I'm going to write this now as a function of r, because it will indeed be in terms of r. 2 pi r, and in place of h, I'm going to put 1,000 over pi r squared. And this can be simplified down to 2 pi r squared plus, let's see, so the pi's cancel. One of the r's cancels, and we are left with 2,000 over r. So now we have the function, the surface area function that we'd like to minimize. And so our next step is to find the critical values. Well, let's just start by taking the derivative on this side. And it might be wise, if you're going to do the derivative, it's probably better to express 2,000 over r as 2,000 r to the minus 1, because then when we take the derivative, we can just use the power rule, and we get 4 pi r, and the minus 1 comes in front, so it's minus 2,000 r to the minus 2, which we can then write as 1 over r squared. So before we continue to find the critical values, or value, I just want to explain the formula from before, because I didn't clarify that the surface area is of the cylinder is combined, it's 2 pi r squared plus 2 pi r h. And I want to clarify that this is because the area of the top is pi r squared, because it's a circle, and the bottom is also pi r squared. And so unlike the open top box problem, this cylinder doesn't in fact need to have a top and a bottom in order to hold anything. And then the 2 pi r h, that comes from the lateral area, which is what wraps around the cylinder, and the 2 pi r is the circumference of the cylinder, which if you sort of unwrap the lateral area, 2 pi r would be the circumference or the length of the rectangle, and h would be the height. So that's where that formula comes from. And here, so let's get back to finding critical values. We would set this equal to 0, and let's see, let's move 2,000 over r squared to the other side, and let's cross multiply. So we get 4 pi r cubed equals 2,000. We divide through by 4 pi and take the cube root, and we would get this, and that comes out to about 5.42. So that there's only one critical value, and now we need to discover whether this is a min or a max in order to fully answer the problem. So now we're at the stage where we consider the domain of values for r, and then test, which of the values, if the critical value is indeed, the absolute minimum, gives the absolute minimum of the function. So let's think about the domain. I think we can all agree that the radius needs to be bigger than 0, otherwise we won't even have a cylinder. And now, in terms of thinking of the interplay between R and H, I'm going to re-express this is the volume formula. I put 1,000 cubic centimeters in for the volume. I'm going to re-express it for R in terms of H. So obviously, the bigger H is, the smaller R. And so if we're looking for an upper bound for R, maybe we need to think about small values of H. So I tried a small value of H. I tried 0.01, and I just plugged that in and found that the radius would be 178 centimeters. Well, if you can imagine this cylinder, it would be basically almost look like a pancake, right? The 0.01, this value here, the height, I was saying, well, imagine if that was 0.01, then it turns out the radius would be 178.4. Doesn't look like it would have a very big volume, but I could keep taking smaller and smaller values of H, and I could get just R bigger and bigger. So it feels like there's no sensible upper limit to the radius. So we won't be using the candidates test because we don't have a sort of fixed interval for R. Instead, we're going to consider the second derivative and see if we can use the second derivative test to answer this. So the second derivative would be, let's see, 4 pi, and then the minus 2 times the minus 2,000 would be plus 4,000, and R to the minus 3, which is 4 pi plus 4,000 over R cubed. And if we think about that, so if we put in our critical value of 5.42, the second derivative will be positive. Well, in fact, for any positive value of the radius, the second derivative will be positive, meaning that the surface area function is always concave up. And if we combine that with the fact that, well, 5.42 was a critical value to begin with, then we can invoke the second derivative test and say that the surface area function has a local minimum at R equals 5.42. And obviously, that's also going to be the presence of the absolute minimum because S is always concave up. And now, so R equals 5.42 is our ideal radius to minimize the surface area. We still have to find the height that corresponds to that. So once again, I'm just using the volume formula here, just rearranging it for H again to find that H is 10.84. And so this leads us to our last step. The conclusion is that the 1 liter can with radius 5.42 centimeters and height 10.84 centimeters will have the least surface area. And this way we can minimize the cost of constructing the can. And that brings us to the end of this lesson. I hope you found it helpful, and if you did, please do click like and/or subscribe to my YouTube channel, Ready to Derive. Thank you.